discussing the second method to find region of operation. The first method I have discussed was a shortcut method or a shortcut trick which you can use in numerical, and this method is basically the standard method to find. So step 1 says find the type of biasing at emitter junction by observation. So we are having emitter junction and collector junction, and this is an operation, right? If emitter junction is forward biased and collector junction is reverse biased, then it is operating in active region. If both emitter and collector junction are forward biased, then it is operating in saturation region. And if both collector and emitter junction are reverse biased, then it is operating in cutoff mode. Okay, this is just by observation. This is the observation method. So step 2 says calculate VCB by assuming BJT in active region. So basically we have to find collector to base voltage. If collector to base voltage is negative, that means the collector junction is forward biased, so our transistor is in saturation region. And if collector to base voltage is positive, that is collector junction is reverse biased, so our transistor is in active mode. Okay, and these values are valid for NPN transistor. For PNP transistor, take opposite values, that is the VCB is equals to positive for saturation and VCB is equals to negative for active region. Okay, so also one more thing is that if beta value is not given in the question or beta value is unknown, then you can take IC is approximately equals to IE. Okay, this thing is valid if beta is unknown. Now let's do one numerical. In the circuit shown, the transistor has large beta and VBE is equals to 0.7 volt. Find the region of operation of BJT. So first of all, by seeing the transistor by observation, we have to find the biasing of emitter junction. Okay, so since this transistor is NPN transistor, and here this is 2 volts and this 2 volt is basically a DC voltage, a DC battery. So first I am drawing a DC battery. Let me connect it to the ground. Okay, so this is a positive terminal. This positive terminal is connected to P type and this negative terminal, which is basically ground, is connected to N type. So here clearly we can see that the emitter junction is forward bias, right? Now step 2 is we have to find the VCB. So guys, for finding VCB we have to apply KVL in just 2 loops, and that's all. Our problem is solved. Okay, so first loop is this loop. We have to apply KVL in this loop, loop 1. Okay, so first thing, just keep in mind that here the transistor has a very large beta, so we can say that IC is equals to IE. Now applying the KVL in this particular loop. So while applying the KVL, I am having -2 plus VBE. Always mention these voltages which are very important. So this is base to emitter voltage, and VCB, that means VCB यानी कि positive terminal कहाँ होगा, collector की side, और negative terminal base की side. Okay, since this is NPN transistor. Now here I will be having IE is equals to 2 minus 0.7 because the value of VBE is given in the question here. So IE is equals to 1.3 milliampere. So IC will also become 1.3 milliampere. Now the next and very important part is, guys, second loop we have to apply here. This will be the outer loop. Okay, from ground to ground. If you're not understanding this part, let me show you what I am trying to say. I'm just replacing this 10 volt with a battery. Okay, so here I'm applying, so this has become a loop. So I am applying this loop. This is the outer loop. Okay, so let's apply this loop. So here I am going from minus 10 plus 10 IC plus VCB, then plus 2 is equals to 0. So let's apply this. KVL minus 10 plus 10 IC plus VCB plus 2 equal to 0. Okay, so we have to find basically VCB. VCB equals to 8 minus 10 IC, and VCB equals to 8 minus 10. IC value we have calculated 1.3 milliampere, and this 10 is basically in kilowatts, so milliampere get cancelled out with this kilowatt, and we are having minus 5 volts VCB. VCB is negative, that means the transistor is in saturation. Okay, so that simple it is. So guys, let's end up this region of operation topic by a small note or a short trick. So which says region of operation can be decided from VCE value also. So here's a short trick guys. If VCE is greater than or equals to VBE, which is base to emitter voltage, and this is collector to emitter voltage, then our transistor is in active region, and if VCE is less than VBE, then the transistor is in saturation region. I hope guys you are liking my videos. And second thing is that just try to apply this trick in your numericals and see whether the transistor works in active or saturation region. Okay, so next topic I will be discussing DC load line and operating point. Okay, so thank you for watching my video, and for the queries guys, please comment me, and please like, share and subscribe. Bye.